So for those in Zoom, I apologize for being late last time. So we will probably have make up on the December. I'll announce on the web, but probably December 4th, which we actually we're supposed to do. But that day, then you will be there. Okay. So let us. So just to remind you, because we don't have further assignment because of I will give assignment for you to do. You can just do your optional. The assignment, because I think we just because of the public holiday and what I just put the assignment there, and after a few weeks I put the solution there. Just that would be optional there. So but if you want, you can just do whatever you like. Okay. So because the question will be in the test anyway. Okay. So if you want, I can give more exercise for you. So today our goal is a little bit ambitious. We'll talk about dynamic games of complete information. Before we go, let us consider quickly review what we have done last time. I mean quickly, I just mean very quick, okay? So static game of complete information, just to recall, very important. One thing is how we define a complete information game in static. It has 3 elements there, right? If you recall the slide, okay? Who are the players? What strategy they can do, okay? And what are the payoff functions, right? So basically just ask who are those people, what can they do, and what consequence of their doing, right? So there's 3 elements there. In all description, you have to remember to describe all possible cases, right? What are all the combination of strategy, what a payoff, right? So remember, the most difficult part is this is something is often omitted, is this part. Here is you have to define all possible profile, which means that for every combination of action, you have to tell what is the payoff, right? Why it's important? Suppose on the case of a firm enter the market, right? If they enter the market, they compete, there's a firm payoff, right? But you have to define if the firm doesn't enter, what is the firm payoff or what remaining the firm in the industry. Okay? Sometimes you may omit when some people exit the market, which is not in the equilibrium, or you specify carefully what are they doing. Otherwise, you can't clearly define a well-defined concept. Okay? And it will be very important today. Okay? That's a very important question. We have to be very careful because sometimes I supervise students writing thesis, then sometimes they forget about those. And forgetting about those can be a big issue, okay? So, but we will be more clear later. And the way we solve that kind of game rely on 2 ways. One way we call dominant solvable, right? Is if something is stupid, okay? Which means that no matter what other people do, this is always strictly worse off. Something stupid should not be chosen, right? And if you know I'm not stupid, right? I'm not stupid, and you know I'm not stupid, then I know you know I'm not stupid, so on and so forth, okay? And continue. Means that that means that the game actually would be reduced to the game where no stupid strategy being chosen, right? Just like dominant strategy, right? If you know I'm not stupid, I always think defect is always better than cooperation, right? So knowing that actually the game reduced to just D and D, right? There's nothing to choose. So that game is called dominant solvable, right? And the other way to do it is to take this extreme. We call iterated elimination of dominant strategy, right? You keep taking away stupid strategy. The game keeps simplified to the game there's nothing left, then we know that's the end, right? But the fact that this is actually very complicated process, right? And you need a lot of practice to know what is stupid, what is not stupid, right? I guess when you're a kid, you play tic-tac-toe. Means this. Tic-tac-toe, right? And at least, I don't know you, but at least for me, up until primary 3, I still find it interesting, right? But Obviously, you know, after that, you know there's a non-losing strategy, right? There's some way to make sure you would win if you get that point, or you will never lose, right? But after that, then, but before primary 3, probably you would still find this game fun, right? But after that, you know there's never lose strategy, right? So that would be telling you that it's not that easy, right? Just like the game Go, right? 围棋, right? And you know it's a little bit, I don't know what happened. Is it something I need to open? Yeah. So that means that even this game would be have something to do. Okay, you would be difficult to follow. Okay, sometimes. Okay. So what it means is even it requires a lot of mental power, and you expect the other guy is also very smart, right? What if the other guy is very dumb, or not smart, or pretend to be dumb, right? That's very difficult, right? Just like, I mean, I think we learn a lot of. Today we see this kind of stuff. Okay, very soon. This kind of thing, doing dumb thing, we need to remove. But the next thing is called Nash equilibrium. Okay, Nash equilibrium simply means a strategy profile. At that point, no one wants to deviate from that. Okay, there's no gain from deviation. Okay, and that we call Nash equilibrium. We don't care how we get there, but it means that once we get there, we stay there. Okay, how we get there is another problem. Okay, adjustment is very complicated issue in Nash equilibrium, but we focus on the case with a very weak concept, right? We don't care about, it's different from the Marshallian clause, right? We know that when the price will be the adjustment mechanism, right? When there's excess supply, right? The price will go down, right? About there. If there's excess demand, the price will go up to equalize the equilibrium amount. But Nash equilibrium don't have this property, okay? There's no automatic adjustment to that, okay? And some equilibrium, there's some stable property. So that's why there's the way how we select equilibrium. But we didn't, I don't think we mentioned in the slide, but there is some way you can pick equilibrium when more than one, okay? And we have already shown that many equilibria there may be no equilibrium, and we show that when we have equilibrium, right, that one way to do it is ensure is if you allow mixed strategy, right, as long as the game is finite, which means that the number of players are finite. Oh, is it too cold? Oh, they said 15, that's crazy. I think we just need, this is 5, so make it 25. We just need I think we just need the fan, right? Not the aircon. If it is too cold, let me know, because I'm walking, I'm talking, so I'm a little bit warmer than you guys. So Nash equilibrium always exists. That's what the Nash proved, and that's actually, I think, this how he get the Nobel Prize for that paper, and that's involved just proving Nash equilibrium fixed point. I think he used Kakutani fixed point theorem, and the history actually said, I mean, he didn't know the fixed point theorem, and he bring that to von Neumann, right? Von Neumann, who is the father of the game theory, and then von Neumann just say, okay, this is just fixed point theorem, and just sent him away. But anyway, this paper made him Nobel Prize, and after that, you can actually almost the same time, De Broglie actually come up with another way to do it. Yeah. All right. So that is saying if you have continuous strategy, right, which is still a finite player but continuous strategy, as long as your strategy is a nice, which is compact and convex, which usually satisfy if you're choosing a number, right? Convex means whenever two strategy combination is also there, right? Compact in a Euclidean space is closed and bounded, usually satisfied in the number. There's no problem. And continuous in other pure strategy, continuous quasi-concave, usually you would satisfy. So that means that equilibrium is guaranteed. And of course, I guess it's not a problem when we do apply, right? Because we find equilibrium directly. There should be no problem. But when you do more, if you want to extend your model, right? in the appendix, people would ask, you have to invoke this theorem, okay? Not you having this kind of theorem is not something that you would you worry about when you first build the model. We build the model, you solve it very nicely, all the closed form, very nice property there. But people would ask, referee often asks, is how is it model generalizable, right? In that case, you write everything in very general sense, right? And then you solve everything in very general form, then you will need it. It is not something you need in the first round, okay? And don't worry, if you actually ever work on theory, your advisor will help you, right? Or your co-author will help you if that technical thing, or you find someone who technical can solve it. So I don't think you would have to worry about that, but you know existence as a big thing, okay? In many cases. I think this already covered last time, so let's go quickly to something to talk about today, because I think it's a little bit too cold, right? I guess. I saw you guys, maybe just open one, that may be better. Because I feel a little bit cold, and it must be your case, I guess. I don't mind, I mean. Now, let us talk about, bless you. So a dynamic game of complete information, okay? So we just dropped the assumption that they move the same time, okay? So what can we see there, okay? One of the important game you learn is called stakeholder game, right? It's a leader game, and just like Conrad, Bertrand, right? Every people set the price and quant at the same time. The famous game is called the stakeholder game, which is one of the leader will set the price of quantity first and order follow, right? For those who do finance will know, a common thing is setting the high board, right? In Hong Kong, basically HSBC, the HSBC is the Hong Kong and Shanghai Bank, right? He will set the price first, had the mortgage rate or the prime rate first, and other bank basically follow, right? Or in the game that talk about the oil, right? The OPEC, which consists of basically largest producing country in the world, and they determine the quantity, right? It's quantity game, it's quantity game, right? And they decide the production target, and other firm would just basically optimize based on that, okay? So because they're large enough to declare, right? And you remember that in the game, the stakeholder game, I think I can mention this again, is the Shanghai marriage market. So you can see Shanghai marriage market. Do I have that? Why I mentioned that? Because well, like this, right? Oh, sorry. And you will see it's not clear here, but you can see this. No, not this one. Why? No. Right. Usually you will see yeah, this one. Right. You will see they will say how old am I, where are you, where we're studying, how much I have with the house, and then they will say what kind of thing she wants or he wants, right? Basically just he set the price, you just say yes or no, right? So it's a stakeholder game, right? Because you propose a thing and then you take it or not, right? So but that is one thing that you see, right? It's not moving simultaneously, right? It's not say it's different from a they call the quick dating, speed dating thing, right? 相亲会, right? It's like bunch of boys and bunch of girls, right? They simultaneously match and tell each other what are the criteria, right? And they simultaneously move. And this is sequential, right? So then you can see things are very different, right? In that case. But anyway, let's don't talk about marriage market at the moment. let's talk about this information dynamic game. So the idea, we focus on the easiest one. We focus on sequential move first. So every point of time, only one person move. And then we talk about we allow people move simultaneously. Okay. The easiest case is, imagine this, right? Is players take turn to make decision, and the easiest thing is the matching pennies games, right? Remember the matching pennies game is in before. Let's go back to that one. It is rock paper scissors, but if you still recall that game, but this is not easy to recall. But let's go back to this game. We call this game, we have no pure strategy, right? Because you can check, because player 1 always wants to be different from player 2, and player 2 wants to be the same, right? Because if this, player 1 wants to deviate, right? And in this one, player 2 wants to deviate, right? No, I don't deviate, right? Because he's super happy here, right? You see here, player 2 wants to deviate, right? If this one, player 1 deviate, right? So there's no Nash equilibrium. And we know the mixed strategy is players randomize over head or tail, right? So now this is basically rock paper scissors, but easier version, right? It just 手心手背, right? It's 黑白配, something similar to that, right? So the question now is, it's easy if I make player 1 move first, right? Player 1 only wins if the coins are different. Player 2 wins if the coins are the same side. Okay, now I make player 1 move first. For sure, you will obviously see what happened is player 2 always win, right? Because whatever player 1 shows, player 2 just show the same, right? By winning the game. Okay, by changing the timing, you change a lot of stuff. And another thing is player 2 strategy is no longer an action, head or tail. It depends on what player 1 do, right? If player 1 shows the head, player 2 shows the head. If player 1 shows the tail, player 2 shows the tail, right? So it depends on what has been done, right? Because the strategy will be a little bit more complicated, as you will see, okay? So it's no longer action only. Its action depend on history or what has been done, okay? So player 1 in this case still only head or tail. But player 2 actually have 4 different types of strategy. Why? It's because given the head, he can choose head and tail. Given the tail, he can choose head or tail. So it's 2 by 2, so it's just 4. Okay, we'll be more clear later, but as you can see, here we distinguish strategy and action. Okay, what can be done for player 2 is head or tail, is action. But strategy involves telling under all the history what can be done. Okay, we'll be more precise later, but do now look that strategy is a more complicated concept. Okay, so have to distinguish about strategy and action. So this is a technical definition for extensive form game. And if you look at this definition, I follow the Rubinstein game theory textbook. If you look at Masco, Livingston Green, they are way much more complicated. Okay, I like this definition because it's much cleaner. Okay, so here is very simple, still depend on n. Okay, but now it's dynamic. So history will be important. So what history? History is just action taken in the past. Okay, you start with the empty history, right? Because action taken one by one. So history is just action been taken, and there is a dynamic, right? Who can move is called the player function P. Okay, and at the last period, which is called terminal history, no one can move, right? So, and what can be done depends on history, right? In the match and pennies game, player 2 can do head or tail both times, right? Same. But in general, what can you do depends on what has been done, right? If you haven't entered the market, so you cannot do anything, right? And the payoff is only at the end realized. So this game only realized at the end. So only go to the end, you realize payoff. But there's no loss of generality here, right? Because you can assume payoff may realize at the middle, but we just care at the end, we count the payoff at the end. That's fine. There's no loss of generality just at the end. Okay. And just to remind you, the strategy is dependent on what has been done, okay? Instead is what kind of action you can take depending on history when you are called upon to act, right? Now the history, player function tell you player I has to act, okay? And what kind of action player I can do is the strategy. Just to remind yourself, right? When the history in this case is player one either choose H or tail, right? So that is, I mean, you'll be more clear later, but don't worry. Usually people don't ask you to define this, okay? But you describe it verbally for this one. Usually, I never see people actually in the paper define something like this directly. At least not the main text. I never see it. I never saw that. But you have to be very clear who can move, what the payoff. Okay. And as I told you, the important part is you have to define for all possible terminal nodes. Okay. So that means that if a firm exits, suppose, then you have to define exit what the payoff for that. Okay. What's the other option? You have to define clearly. Otherwise, it's not. You cannot define equilibrium. Okay. Which will become more clear later. So the two things here, outcome, right, is the strategy profile, okay, that end up there, induce that, right? Because based on a strategy, right, you will induce the outcome like head, player one choose head, player two choose tail, right? So that's the outcome. Or sometimes outcome is depend on the strategy choice by player or what are the payoff, right? Equilibrium payoff. So next equilibrium the same before, no one can deviate. But remember the strategy is more complicated. Okay, we'll give example, so don't worry. We'll try to tell you what it is. Okay. So consider the matching pennies game, sequential one. Player one move first. So player sets 1 and 2. Okay. And time actually 2 player move, well, one after the other. But we will start with time 0, which no one start yet. So at that case, the history start at empty set. Okay, empty set. And player 1 can choose head or tail. Okay, and this is his strategy, right? His player 1 strategy based on the now history, he will choose head or tail, right? And player 2, right, would after player 1 choose head or tail, right? And the history is either XX or XT, TX or TT, right? So the history of the terminal game can be either 4 outcome, right? And all possible history can be like this. Okay? So I hope this will clarify what do you mean by history, right? History is all possible outcome, right, along the path, right? Not just end, but you also tell about this. Right? So have to be very careful. Also the now history there. You don't worry about the formality, right? For this, the formal symbol just help you to clear your mind, okay? And you don't have to write that down when you actually write the game, as you will see in my future example. Okay? As long as it's made clear, you are clear, then it's fine. Okay? You don't need to write that down. Okay? And player function, you to tell under the now history, player 1 will move, right? And under H or tail history, player 2 will move. Okay? And what are our action, right? Under history now, okay, which is player 1's move, player 1 can choose head or tail, right? And after H or T, which is player 2, right? He can also choose head or tail. Okay, so everything is the same in this case. And you can define under HH, right? Which actually, and TT actually, player 1 lose, right? Player 1 different, right? -0, -1, right? And player 2 wins. And if they're different, right? And player 1 wins, right? So that would be the game. Okay. So this complete description, as I said, you would never do it in this way, but just to clarify the symbol, right? You probably ask, what is the way you would do in actual practice, right? So basically, you just tell them, right? You write, this is the game, right? And tell them, pay off, and you're done, right? Because this tells you the game who would move and what they can do, right? But writing in the Word, as I said, you have to be very careful to define the payoff carefully, right? Because when you write the word, sometimes you miss some history. So you have to make sure that you have to specify all possible history, okay? So that is something that you have to be a little bit more careful, okay? So this is usually you will see more often, indeed, in the game tree, okay? This is something you will draw, and this is indeed a complete description of the game. So usually this is what you see when you see the journal, say management science or other journal marketing science. This is the graph you will see, okay? Instead of doing this complicated stuff, but at the background is there, right? So we start with now history, right? Now history mapped to who is moving first, player one, right? And player one can do two strategy, H and T, right? And after that, according to history, who is moving, right? And what are possible action they can take, right? Under possible history, and what the payoff, right? And I have circle is the terminal note, right? So everything is very clear. This is player one payoff, the player two payoff, right? So you actually has all the description, right? Who are the player, right? What are the history? Because you go up, and it's all the history, right? And who can move, right? And what the payoff? What terminal note, right? And what the strategy, right? Strategy just collecting what player two can move and chose, right? So everything can be described by the tree. So tree would be the most essential thing you should be able to tell, okay? Now, the strategy, right? Player one can choose head or tail, but player two is under head, what he can do, under tail, what can do. So that is a two by two. And the strategy profile and outcome is very complicated, right? Because there are two possible choice for player one and four possible choice for player two. So there are 8 possible outcomes, right? So a lot of them are redundant, but we really need them, okay, to be formal. Now, what is the difference, okay? And as we said, the sequential move, the simultaneous move, our prediction is there are no pure strategy equilibrium, right? And the equilibrium is randomly mixed, half by half. And what is the outcome in this sequential one, right? We know that there is a Nash equilibrium, right? We expect the equilibrium will be pure one, depending on what player one do, right? If player one do head, player two will do tail. If player two do tail, player one do head, okay? There's no way even the player one randomized, okay? Player two will do the same, okay? So we actually, the prediction is very different, right? And actually in this case, player two always win, regardless of the outcome. The outcome is all player two always win $1, right? So focus on Nash equilibrium is problematic, right? Because what player two actually would do would depend on player one do, right? Which is not covered or captured in the static game, right? So we, in this case, right? Player two will have a dominant strategy, right? If he has to choose, right? Player two will choose 1 over -1, right? This is his dominant strategy, right? If here, player two have dominant strategy choosing tail, right? Given the head, tail, player two will choose tail or the head, right? Right? So you can see in this case, the dominant strategy approach will actually lead to different thing from Nash equilibrium, right? Before we said dominant strategy and Nash equilibrium the same, right? So now slightly different, right? So how can we resolve this kind of problem? Is to focus on the case later you see cost of gain perfect Nash equilibrium. But before we do that, we consider game since B school. We talk about game that we think that is very often used. It's called prediction game. The setup is like this. There's an entrant and incumbent. Okay, the entrant decide whether in or out, or get out. When I get out, then the incumbent will become monopoly, right? If in, the incumbent will actually whether fight the guy, start a price war, or just peacefully, okay, accommodate. Just peaceful of price war, okay? And if not enter, so I have to define where pay off very carefully. If the entrant decide first, right? If not enter, the payoff is 0, okay? And if enter, okay? And sorry, the payoff would be 2, right? Because he enjoyed the market profit, okay? If it enter, if they peacefully, they share the $2 there, okay? If they're fighting, okay, it's very costly, okay? You'll be even worse for them because price war. Incumbent lose $1, entrant lose $3, okay? So that's the game, okay? I specify who move first, the payoff, or action is very clear. So this is something you would expect you to write when you write your own paper, right? Write your own model project for your class, right? For our class, that would be something I expect. I expect to see this, okay? And of course, you can write that as a normal form game, okay? Because it's static game, and we will see what happened, why it's wrong, okay? In normal form game, we can see the entrant can be out or in, right? The incumbent actually can fight and accommodate, okay? And of course, if out, then nothing actually incumbent is doing, right? Nothing really matter, okay? In this case, out is actually 2-0, right? Because regardless of the incumbent want to fight or accommodate, there's nothing he can do, right? Because the game ends already, right? It's out, then no need to fight. Okay, it's there, nothing, right? When in, there's a payoff, right? So if you look at this game, okay, what are the equilibrium there? Okay, remind ourselves how to check next equilibrium. Check every possible outcome, whether there's deviation. Okay, we have to go through every single entry. Okay, so sorry. So now look at this one. See if any deviation kicks in. Okay, now check player 1. Is he want to deviate? Is it 0 to negative? No. Player 2, will I want to do the 2 to 2? Same, no deviation. So this is next equilibrium. Okay. Now we check the other one by one. As I said, go one by one. This guy. Player 1, is it want to go down? Yes. So this is not. And now go to the other one. Check this guy. Player 1 want to go up, right? No. And finally, last one. Player 1 want to move up? No. Player 2 want to move there? No. So this are the 2. Okay? So just remind yourself how to check. Okay? Check every possible outcome. Let me repeat. Every. Okay? So don't be lazy. Have to check everyone. Okay? Now, are we saying that these 2 outcomes are equally plausible? Okay? Okay? If they are not that smart, then might be. Okay? You will predict that. Okay? That will be our prediction. But I think it is not clear why this is the case. Because suppose the guy come in, okay, in the game. Now the incumbent has decided whether to fight or not fight. Okay? Okay? Now the question is already in, right? Suppose the game is already in. What do we have? There's no more out, right? In this scenario. Okay? Are we expecting incumbent to fight or not fight? Right? Right? Fighting is not feasible, right? Right? So, do we expect this will be chosen when they actually come in, right? This is basically coming, is called empty threat, okay? Or not credible, right? So it's not entering because you say, if you come in, I will fight, right? That's what happened. If you see early this year, we have last year, with Russia and Ukraine, right? And Russia often said, if I was attacked, I will nuclear bomb the world, right? Or if you going to do this, then I'm going to do that, right? Then this will never happen, right? Right? So that's why it's empty. right? Empty fact. They don't really believe that, right? Right? If just like don't come, right? If you come, I explode, right? Just like when I think in the old days, probably not now, is when China, right? When people try to collect the land from the farmer, right? Or collect the land from there, right? And then if you come, then I will kill people, or I will just got crazy, right? And sometimes you have to make yourself credible, right? By putting the gas, right? Or putting some crazy thing in the room to make it credible, right? But it rely on the fact that if you do something, I do something crazy, right? But do you believe this is crazy, right? If you can make yourself believe you're crazy, then you're fine, right? And something probably many of you might know is a movie. I think many of the ladies may like. It's probably you see this, right? So so I guess it's a famous, not here, but oh yeah, this one, right? The famous saying is, "You jump, I jump." Is it it's a natural equilibrium? Is it credible, right? Suppose if the rows, I guess, right, jump, is it right for what's Leonardo name? Jack? Is Jack going to jump? Is it the case? Do you think Jack would jump or not? If you're Jack, you jump? If Jack here, is it Jack going to jump here? Right? But that being said, if Rose believed that Jack would jump, then that's equilibrium. Okay? So you have to, whether this is believable or not, really depends on whether you believe that, right? But in general, if you think they're sophisticated, okay, that should not be there. Okay? That is not that's based on empty threat. But of course, in the real world, people try to make it credible, right? And something like right, it's like what the Putin done, right, in Russia, invade Ukraine, and he just when he don't want to back off, right, he write it in the constitution, right, this is our land, we never back down, right, something like that, right? Or when people go to war, right, and never back down, right? I think probably you remember one of the romance in the Three Kingdom, right? And when Guan Yu, right, tried to fight Pang De, right? And then when he fights and the guy Pang De, right, carry 7个棺材, right? And then just to show that he's willing to die, whatever, right? And probably this is one also very famous, right? I think 10 years ago, when Premier Zhu Rongji, right, and he want to fight the corruption, what he said is, I prepare 100 guan cai, 99 for the corrupt official, one is for me, right? So it's just kind of credible, right? Because you would think when he actually do things, right, is he credible or not, right? So that is the idea. So so this is our prediction, okay? What we call is called backward induction. For those who do operation research, that is a very well-known concept, right? Which means that you would try to look at things from at the end, okay? Backward induction, okay? Is look at the last period, last one to move. What is optimal choice, okay? And if the incumbent look in the fight, okay, come in, then with the fight accommodate, right? And of course accommodate, okay? If that's the case, we go back once forward, and this is gone. So entrant decide this or that, right? And of course enter, right? So that would be the prediction called backward induction, okay? And I guess this is a very powerful concept, backward induction, in the real world context, right? And actually, that's what actually you should do. Actually, I learned from a very good game theorist, right? Often, after this, let's have a break, is how you make decisions over time, right? Many of you think, and when you, probably many of your year one PhD student, right? You ask, what kind of paper or how you should proceed to do your research, right? You wonder, oh, should I do theory? Should I do empirical? Should I do this topic? Should I do that topic? So on and so forth, right? One of very senior colleague that I was in Singapore, he told how he advised students is by parallel induction. Imagine now you're in the market, 5th year down the road. What are you going to do? Are you going to be academic? Are you going to go to industry? Are you willing to go back to China, go to Japan, go to whatever you want to do? Then you know what you need to have, right? Suppose you want to be industry, right? You have to get the skills that require you to get in industry. Work on the paper on those, do more applied topic. If you want to be in academic, you should do more academic challenging job. Do challenging paper, right? You have to prepare for that. And go back and then determine what classes to take, what research you have to do to done, right? Everything is parallel induction, right? And also people from philosophy, right? Talk about how to think about your things in your life, your sanguan, right? And decide how to value stuff, right? Parallel induction, right? At the very end of your life, assume you die, you care nothing, right? Then you think about, at the very end of your life, how you view your house, your money, your kid, and go backward and backward and backward. You know how to view stuff, okay? And backward induction is powerful, as we will see later. And later, let me finish this one, sorry. Is called subgame. Is you would think a game, if it can stand by itself, okay, you can solve equilibrium in this smaller game, okay? In this particular case, you can imagine this is a own subgame. It's a game by itself, okay? And you can solve Nash equilibrium in this model, okay? And what we call subgame perfect equilibrium, proposed by Shelton, is that we have Nash equilibrium in every subgame. That would be called subgame perfect, okay? What does that mean? Now, if player one, so incumbent have to choose, this is the game he's facing without the first roll, right? Tell us what is the best strategy, okay? And that is equivalent to, turn out to be, same as parallel induction, okay? So parallel induction is isomorphic to subgame perfection. So basically, we solve the game by looking at the very end, okay? Look at what people would do and go backward, okay? So of course, it assumes a very strong rationality. We have to see through the end of the world and come back. What to be done, right? Right? Then, but as long as people are smart enough, this is our prediction, okay? So that is called subgame perfect, okay? So I left you, we talk about this after the break, okay? Let's have a short break because I think it's a little bit too long. Let's have 15 minutes break. You reply, enjoy yourself for the stuff, okay? That reduce my queue a little bit. So let's have a break of 15 minutes. I open the you reply, then you can tell me I want to try that as well. Oh, no more? Open more, open more, open more, open more. feel free to take a. Yeah.这两个关一下吧，打一下开。不然，不然。So we resume at 10:40.小的最爱这个是。
然后我们还可以做沙包。就菲律宾联邦，就菲律宾联邦三个学校。可以买个赶紧吃，对，下午睡觉可以。朋友结婚，然后没有，我怎么都结婚了？一堆朋友都结婚了，今年。那就菲律宾就基本上大部分都今年。对呀，今年已经，而且也是我今年去的。我身边是有朋友结婚，但我感觉很少，特别亲的朋友，没有朋友，再等不了3个月就开始。哇，我有一个朋友，他谈恋爱，但是我感觉他谈恋爱之后就是发小，这个就关系很好，谈恋爱之后像是，不是谈恋爱。北京冷吗？冷，挺冷。其实我穿了很多的，没什么。因为上个周末我也在北京。啊，你在北京？对。我感觉还挺冷。在公司，我都穿羽绒服。我穿羽绒了。而且那个对本地人说穿羽绒小是不是？我觉得真的，其实感觉南方的衣服也蛮好。就是我在大街上，我不那样，我看对面走过来穿着小燕子，看你来一个。嘴边吹人一月，我穿短袖的，直接抬着。哦，走屋里面。你在抬一个。而且很干。北京是不是也可以就羽绒服里面穿点袖子？对，我在家穿短袖。有没有去玩？去了。去玩？不是，我是北京人。还有半个周一晚上去，本来是周天回来的，错过了最后一班飞机。看到了没？哎呦，就差几分钟就可以开走。不开，对，5点，他是5点半的，5点31，对，他这个比较有上场的地方。那。但是都是不动。都很好看，他不动，我被人夸，不能夸。而且这个很痛苦啊。在手机上。对。对，手机上很痛苦。而且问题是，但是现在是他们前面的车就是越来越好。在日本人不动，对。有点生气的。没几分，1个半小时，现在我跟他就1分钟把我。不是我心。我是大兴，虽然很远，但是不堵车。对啊，就是东三环路非常堵。你知道短东三环？对。我应该做就是这个交汇说的比较大。对，就还很远，但是不堵车，很少。但这市区可以差不多1个小时，1个多小时。我们还有1个多小时，但是。没有钱，没有钱。今年放我定了不少。这个本地人没有钱。他们说3年没有出国。确实。所以没办法。是北京。不是讲那个什么北京什么健康宝。对啊，就是去遛狗。对。很多什么人寿男的。没有立马的。没有，都取消了。这个东西没用的。我也觉得没用，没有。对，你都是随便写。从这去深圳的时候，你说一堆人排在那里扫那个码，这样很没有用。 罗湖或者落马洲。落马洲就是你去市区，就是比较高端的地方的话，会到很偏区，就是去 shopping 就是去落马洲。对，如果你要去广州的话，就是去罗湖，就坐火车去广州就去了。日本南站是哪站去的？广州南站吗？南山区啊，那就去。就是消费开始跟很多周一我们去的，还有周二有回来。但是如果我坐地铁的话，去南山只是去那个深圳湾，对，再加车去深圳湾这样子。哦，那深圳湾可能真的很小。所以我们在就是落马洲的，落马洲的。这个变压了，进去的话有一个正常的事情。那不好都不要，我觉得真要我不要这样子转上去。落马洲就是你下地铁，然后下个电梯，然后直接一条非常对，但是过去那个天桥就很长，但是它有电梯，可以整个电梯都很快。这是在第几种？它是在第几种？对，我以前。我第一个就是台北，都不懂，所以我不懂那个第一次去的时候，总共3年的。都马都是我觉得。
下一追。Yeah, thank you very much. I hope you have a good break. So let us continue. Let's see. Final exam will be take home. So I will put the exam on the blackboard. Give you 2 weeks to do. I hope you do it within 2 hours, but I can't check. So but I think 2 hours will be sufficient for you to finish the whole thing. So I put it, I'm done, but I will put it like next week because I want to finish everything before I put it, right? So next week, I think we finish the main thing, then we put there. Of course, I remember next Wednesday we have makeup. Makeup will be cover, I think I will cover principal agent problem. For accounting, I think please attend. I mean, or at least watch the video. It's very useful. The scope, well, it's just probably up to next class, but it's take home whatever. I mean, the scope is, you know, right? You will see you will see it. Is that okay? I hope that's okay. It's take home. Due to the project, this is something I want to ask a little bit. What was my supposed due date? What did I write? Let me check. I really forgot because this semester is too busy for me, so I don't remember all the day. Course outline. Did I put that there yet? My mistake. I didn't even put that thing. The project. So let me put the project later. So I can take the last year project thing is very similar anyway. So just since you asked that, I probably mentioned that as well. So the project likely I put the same thing there. The project is likely you would either, maybe just put here, I put the same thing on today, later. So either you write a paper, some people do because you're actually working on paper anyway, or you write a proposal, what can be done, just describe it, okay? Or you want to write a literature review on the theory based on, say, if you're finance, you do some recent finance paper review or some topic, okay? Because I want the project to be useful to you, okay? So you just work on the thing that's useful for you, okay? Or you can pick up, you can like a reference report, right? Pick up some paper there and just write detailedly what can be done. It can be done anyway. Or you want to pick up an empirical paper. In the recent paper, you want to write a theory model. That's also fine. So it's very flexible. Or in the case you don't know what to do, just email me. We can meet and we can talk what to do. Okay, so don't worry about that. And I think I plan a lot of stuff, so I just don't do it. So basically, you just do whatever, just send at the end. So I guess what I actually ask is, I think it's 5 to 10 pages long. Yeah, I think 10 to 20 pages, double spaced report. I make it 10 to 20 means I don't want you to write too much. Okay. 10 to 20 is like the rough idea. I don't put lower bound because I don't want you guys to be in personal dilemma, right? You can, whatever you think is good, you just do it, okay? Because you're a PhD student already, right? So learning is your own stuff, not me, not for me, okay? Not for yourself. Just do things that is important for you and just do it, okay? I put there, okay? I'll put a little bit more detail later, but it will be similar to this one. So just write down stuff and just try to write paper, okay? And he'll tell you what to do, but I'll put that later. Try to change a little bit, but this is more detail on how you do stuff. But so I hope kind of answer. And when to submit? I guess now is 20. Then I give the exam like next week, so maybe mid of December, somewhat like that. I mean, should be fine, I guess. Is it okay? Is it not enough? Maybe before Christmas. So is it before Christmas or after Christmas? After Christmas, okay. After Christmas, and then you give me. Okay, after Christmas, then I will have that. In the worst case, you don't really know what to do, just email me, schedule a meeting, or just email me. We can talk a little bit. You can just talk by email or talk in person if you really want to talk about what to do. But I think we are very flexible in that project. So try to make you apply what you learn in your own academic context. So if finance, you just pick up a paper, you write a paper, or whatever that related that's useful for you. That I'm happy. Okay, just want you to learn actually what to do. Okay. Yeah, that's basic class. Everyone knows what to do. Oh, we have consensus here. Yeah, you jump, yes. You jump, my jump is it subgame perfect? So the question is, the answer is no, unless Jack is crazy about rows, right? If you care, then it makes sense, right? And yeah, barrel reduction dynamic game theory, yeah, that's true. Yeah. Oh, I'm too fast? Okay. I don't know. Is it too fast? Okay, that's fine. Yeah, good luck for everyone. I guess our class is not very demanding, right? So hopefully that you learn something out of it. Okay. So let's go back. So we are now seeing that how do we solve this kind of game? It's what we call subgame perfect or barrel induction, right? Basically, you just look at the last period, solve the game, and go back. Okay. So let's see the example. I mean, although it looks very innocent, right? But when you actually do it, you turn out that it's not that easy. Okay, so look at this. How many subgames are there? Okay. So first, probably look at what the strategy said. Player 1, 2. Player 1 is very simple. You just move, just A and B. Right? But player 2 is more complicated. Player 2 has actually 2 nodes. Okay. So her strategy will be this multiplied by that, 2 by 3, that's 6. Right? You have CF, CG, DF, DG, EF, EG, 6, 3 times 2. Okay? So I have to be very careful on this one. And what are the subgame perfect equilibrium? As I said, subgame perfect, same as barrel induction. So let's solve it by barrel induction. Look at the very last subgame here. Subgame means I cut it out, it stands by itself, right? It can be in here, if you start from here, this is the game, right? There's a now history, everything is nice. That's a game. So whenever you can call a game, it's a game. Okay? Here, what to do? Okay? You're player 2, you would do C or E, right? Same to you, right? If your choice is either C or E. Is that clear? Okay? Now go to here, player 2, F of G. What you would do? Obviously, between 2 and 3, what is clear? G, right? And now player 1, okay? Parallel induction. So parallel induction have to be a little bit tricky because of 2 choices here. Okay? So you do 1 by 1. Why? Same as natural equilibrium. We check every possible scenario. So let's focus on the case C is being chosen. In that case, what is 1 going to do? A or B? Okay, suppose the case, let me circle that now. You focus on the case of C first, okay? So 1 is looking at 1, 2 or 1, 3. And the case 1 is getting 1 anyway. So it doesn't really matter. So that means that this is 1 equilibrium. For this one, choosing A, choosing B is another equilibrium. So 2 equilibria already. Okay? And consider a case where E is being chosen. If E is being chosen, now player 1 is choosing between 0 or 1. Then we just 1. 1 equilibrium here. Okay? So let's write down what an equilibrium. Equilibrium is set of strategy, right? So I have to be very careful. Let's write that down. So when we said if 2 choose C and G, right? Remember player 2 strategy is 2 things, right? C and G, right? And player 1 will choose A, right? And if player 2 choose E and G, oh sorry, C and G, there's an A here, right? But also there's another one, right? It's also B, C, G is also right? B, C, G. Okay. If player 2 strategy is E and G, okay, the choice is just B, right? So that will be 3 subgame perfect equilibria. Okay? And remember, subgame perfect equilibrium is defined as strategy, not outcome, not payoff. Okay? Let me repeat the very important. Subgame perfect equilibrium is a strategy profile. A strategy, not the outcome CG, not the outcome AC, okay? Not the payoff 1, 2. No, not payoff, not outcome. Okay? We will call equilibrium payoff is 1 and 2, right? Equilibrium outcome will be AC. Okay? Equilibrium itself is the strategy. So equilibrium is very complicated. Okay? Have to be very careful how to define those. Okay? Now, I think I already had a solution in the text, so I don't need to worry about that. You see already. Okay? So so one minor thing is we would sometimes call the original game is called a subgame, but it's not we call proper subgame. Okay? So when you see the proper subgame, it's not including the whole game. Just this is the subgames. Okay, but the whole game is not the proper. Okay, but it's still an improper subgame. But anyway, just terminology here. So as we see, and I said you jump, I jump, right? So this is the extension of you jump, I jump problem. Okay, look at this problem. Okay, player 1 and player 2 take turn. Okay, the process is the following: there's $2 on the table. Okay, and in each period, there's some money generate. Okay, or stop. Okay. It stopped, then it don't generate any money. And this is some payoff, very weird. Okay, anyway. And if you try to run this game in an experiment, okay, well, let's see what the game here. Okay, what is the game here? Okay, if you do subgame perfection or parallel induction, look at the last game. Okay, Player 2 doesn't really matter what to do, right? Whether C or S, the same, 8, right? Doesn't really matter. But now look at once before. What player 1 will do? Player 1 will choose stop, right? Because stop give him 7 instead of, then this is the choice, right? So you can do this, right? You can write, usually you will solve it this way, right? So now go back one step, backward, what you will do as a player 2. Player 2 is choosing between 6 or 5, right? Because choose this then this is the case, right? Because 6 is better than 5, right? Is that clear? Now go back one step backward. Player 1 is choosing, right? Player 2 will stop anyway, right? So player 1 will choose stop, will give him 5, continue, give him 4, right? So he will choose this one, right? So this is the case. And go back further, right? Player 2 is choosing either 4 or 3. This again, okay? At the very last, the whole game, player 1 is choosing between 2 or 2, doesn't really matter. Either they stop or continue, okay? Will be equilibrium, whatever, okay? And doesn't really matter anyway, right? So you will either end up here or here, okay? And you will see in the experiment, actually people are not that selfish. Some you will see somewhere in the middle. Okay, and but equilibrium will say this is being chosen. Oh, I think. Oh, I think this would be 4. I guess it should say. I think this is original setup. I think a typo here. Should be 4 here. So should be 4 here. So the only thing is stop every time because that fit the idea $2 grow at each one. So this would be 4. Okay, sorry for the typo. And the prediction, right, will be just S. Everyone choose S whenever it's given a chance. But in the real world, usually you will get somewhere in the middle, right? Because you expect somewhere go to 4, right? So it's reasonable, okay? So, and probably the problem is what happened when why we talk about backward induction is not right. It's because I think people cannot think too far away, right? You see the game, do you actually look at solve by backward induction? Probably not, right? Might be if you play this enough, then probably might be, right? But the fact is, usually in the experiment, people don't go that far. But this is a game. It's a very famous game. What is the moral of this story when you apply your word in application is backward induction is a very strong concept, right? And when you say someone moved before the other, it's a very strong argument, okay? So only if you think that is the right thing, then you solve backward induction, right? Otherwise, you consider simultaneous move, right? So by calling someone a stack over leader, it's very different from a corner game or Bertrand game. So you have to be very careful how you make the timing. And that's happened when you write paper. People will complain your timing. Okay? You will say, you moved it, why this firm moved over the other, right? And you have to justify. And you might try to argue, oh, if they move same time with a similar solution or reverse similar solution, then it will be fine. Okay? You should expect your model will be robust to the timing. If not, you should justify why your timing is made in such a way, right? So that's very important, right? You cannot just say, I write this model gives me the result, it's simple, that's why he moved first, right? That's not the right way to do. You have to say, either it's robust, right? Or you have some reason to justify. So when you make a timing, always always asked by referee by that. Of course, if you run regression, then you don't need to worry about that. But okay, is that okay so far? I think we have now how to solve the model. So now we have simultaneous move. Okay. So the only difference here is you allow people move at the same time. Okay. So its description is very similar, right? The only thing is here is who is the move. It's no longer n is set of players. Right? It's 2n, right? It's a set function, right? Set of players can move. Okay, and the action will no longer be action will be product set, right? Who can move, what they can done. Okay, the only difference is here and here, right? Other thing, nothing different, right? The only difference is who can move, involve more than one player. What can be done, more than one player. That's it, right? Of course, as I said, you would never actually write that down, right? Formally, but you would implicitly in your writing make it clear. Okay, if you are not clear, then no one will be clear. Okay, but as I said, in most of your application and my application, usually I just draw a tree, then you'll be fine. Okay, let's make the most simple thing we call simultaneous move game, the matching pennies game, the same, right? How do we define that, right? We know it using a static form, but this is very simple, right? So let's see the game tree first. Look like this. We'll draw it this way. But let's go back to here. What we do is 2 players, okay? And the history is again the same, right? But do note that different from the previous case, there are no history of H and T. Why? Because they move at the same time. Okay? History is much more simple. Okay? And player function is from the beginning, 2 guys move together. So the 2. And this action set or strategy set, right? The action set is like player 1 and 2 move from the null, and no one move from the term. These are terminal. So just only have to specify non-terminal history, right? Just what has been done. Very simple, right? And I guess the payoff will be very simple. I think you have seen that, right? The payoff is this, right? So how to draw this in the game tree? We want to draw it. We will call the information set. Okay, information set means that player doesn't know where he is. Okay, then the subgame, when we draw subgame, we cannot cut through the information set. Okay, it will become very clear later. Okay, I will define immediately. Don't worry, it's not complicated. Okay, this is what we call the simultaneous move game, matching pennies. Okay, the only difference is I draw information set here. Why? It means that player 2 doesn't know player 1 choose X or T. Okay, he just know. Okay. Up to here, something has been there. Okay? And that means when we call subgame, we cannot cut this out. Why? Because this is not a game. Because player 2 doesn't know where he is. Okay? So as long as you can solve, all the game will solve the same. Okay? There's nothing new there. Okay? How do you solve this game? Because this simultaneous move game, we can just solve as what we done in the last class. Right? Just write down the matrix and solve it out. Okay? So that is very simple. Right? So basically just combination of backward induction and what we learned in the last class. Right? When they move together, solve the way we learned last class. When people move sequentially, right? Then it's backward induction. Okay? So we will do one by one, so don't worry. So this game. So let's quickly look at what are the strategy for player 1 and player 2. Okay? Player 1, you can see he can choose A, B, C at the beginning. Okay? But also you have to tell them F or G. Right? So that means that is what? 3 by 2. Okay, 6. Do note that player 1 cannot choose F and G. It's either F or G because he don't know where he is. Here only one strategy, F or G. Cannot do GF, cannot do FF, right? When you do F, it's same, G is the same. Okay, only two choice. Okay, so F, so it's A, B, C, or F and G, so only 6. Okay, what about player 2? Okay, oh, by the way, you would wonder why I have 6. You wonder if player 1 choose C, right? Why player 1 still choose F or G, right? That's a question you ask, right? The reason is if I don't specify what player 1 is choosing, then I don't know how to check deviation. I don't know how to check whether this is equilibrium, because I need to check player 2 whether they're doing the right thing, right? So that's why we have to specify all possible history. So that's also an important thing, often omitted in your many papers, is to specify, even though it's not there, what a payoff. Okay, because in the check. And player 2, the strategy you either DNE and XIJ. So it's 2 times 3, 6. Okay, so to be very careful. And probably you ask, how do we solve this game? Okay, is we go subgame perfect, right? So you will tell how player 2 choose here. Okay, of course, compare J, L, and M, then you know what to do. And go back to here. This is another subgame, right? And this is very easy. Just solve like what we do last class, right? Because player 1 choose F or G, and player 2 choose D and E. You can just write the matrix and solve it. Once you solve this, player 1 just choose A, B, and C, which is the best one, right? So that's how you solve the game. Okay, that was induction. Okay, and I have to remind you once again, you need to specify, player 1 has specified A, B, C, and F, G. Okay, even though C is there, choose this. Why? Because then you can know what 2 is choosing, right? And then you can see whether 1 will choose A, right? Because in order to say C is equilibrium, you have to check whether 1 actually wants to deal with A, right? Without specifying what 1 do, you don't know what 2 will be doing is optimal. Okay, so that's why that's the reason. Now go back to another one that is even more fun. This is what we call the niche entry niche game. Okay, here is entrant decide out or in. Okay, once in, they would decide which area to focus, whether focus on large market or small market. Okay, this is like the anti-coordination game, right? If they focus on the same market, they fight. If they're different, then they would be gaining, right? Because you focus on own, you don't compete. Okay, so out is 0, 1. Okay, and if player 2 is the entrant, the incumbent, right? So if they're different, small and large, right? They don't collide. Player 1 we got 1, right? Enter still a little bit costly, right? Because entry cost, lost 6, lost 1. Okay, because the entrant choose a small market, right? So lose some money, right? If they fight, -6 for them. If the entrant choose the large market, right? The incumbent choose small, then losing $1, right? If they fight in the large market, right? -3. Okay, so there's a payoff. So how to solve this game? Okay, just to remind yourself, we will do barrel induction. Okay, so you have to decide how many subgame there first. In this one, only 2 subgame, right? Or actually 1 pop-up subgame. So look at this. This is a 1 subgame. Okay, and tell yourself that this is not a subgame. Why? Because it cut through the information set, so it's not. Okay, so there's only 1 and there's a big one. So that means that barrel doesn't imply we have to solve the game 2 times. Okay, very tediously, right? But let's solve this game. Actually, this game, as we said, this is called an anti-coordination game, right? They will not collide anyway, right? But let's do it. Let's actually write down the game tree first and solve this out. So this is the game, okay? And when we solve this, this is a normal form game. Let's write that down, right? And check. How do we check this? Check every single outcome anyone would want to deviate. If no, then done. Okay? So check 6, anyone deviate? Yes, because entrant want to go down, right? And check this guy, okay? Want to go down? No. Want to go left? No. Yes, right? And check the other one here. Want to go up? No. Want to go right? No. Yes. Lastly, check this guy. Okay. -3. Want to go up? Yes. So no. Okay. So that's how you check. So 2 outcome, large and small, small and large. But you predicted already because this is anti-coordination game, right? They don't want the same, right? So that's what you predict, right? They will separate themselves. That's what we call the marketing people, market segmentation, right? They segment the market. Now, go back to before, okay? Remember, we have 2 possible outcomes from the subgame, so we have to solve one by one. Consider the case where we have the small firm go to the large, the big firm, the entrant go to large, the incumbent go to small, will be this one, right? So you go back, right, replace it, then you see whether entrant will enter or not, right? And entrant compare 0 or 1, right? Of course 1, right? So the outcome will be in, large, small. Okay? And in the case, this is the entrant, it will be small, incumbent large. Okay? And compare 0 and -1, right? It will be out small large. Okay? So now we have 2 subgame performance equilibrium. So can we have more reasonable prediction? Can we have more? So which one you think is more likely? So based on subgame perfection, you can't tell. But from other things, can you do you have any prediction? Or you think both are likely? Okay? I will not ask for this for econ student, but since you're B school, you could be able to tell me which would be more likely. Which is more likely? The right one, right? Because you would expect the incumbent, okay, likely to do something more, right? Likely to can focus more, right? It's likely to commit, what we call commitment, right? We can say, I will do large whatever, right? He can make the announcement, he can make the way that make the entrant to believe that actually signaling, showing that, try to make sure that I'm doing large whatever, right? I spend our research on large, then this will be natural outcome, right? So that's why it's sometimes what we call the entry deterrent, right? We don't talk about this right now here, is we'll be talk next week, is trying to show your strength or try to signal your will, right? By doing things in advance or do crazy thing, right? Suppose how I commit, right? A big thing, big firm will be, I fire the manager that is doing the small market, okay? So that means that when you come, you know I'm going to focus on large, right? Or I remove any product that actually cater for the small market, right? Then you know when you come, I just do large, right? They actually do, right? But of course, this requires a commitment, right? Or you do something like, actually, the argument is like, this is not a game they're playing, right? You're saying, indeed, the incumbent actually can do something, right? Maybe do something costly to change the game payoff, right? Or to signal it, that's a large thing I'm doing, right? Or the thing is like, what I mentioned is, you just make sure that choosing small is very costly, right? So what it means is like in this diagram, the argument is like for the incumbent, okay, to choose small is very costly. So just make this very negative, right? Expect to make this one, right? Maybe make it -6 as well, right? Then so that you know this no longer equilibrium, right? That's usually how change the payoff, right? Try to burn, they call money burning, right? Burn the money, right? I just fire all people who cater for small market, right? Just like suppose you are a firm in Hong Kong, right? Suppose Hong Kong and Kowloon is the big market, New Territory is a small market. So what you do as a firm, just close down all the shop in the New Territory, right? So you know if you come, I just fight there. You don't want to compete with me, so you go to the outlier lion, you fight there. I give you that, right? I just say, okay, I focus on this market. Okay, you know what to do, right? So implicitly, they will just try to do things like this. Okay, so but that is a little bit advanced topic. But you can see there are a lot of things you can see how you change the model, right? How the firm try to change, right? This sometimes they call strategic management, right? You see the game, you try to change the payoff, right? Try to make your opponent to do other things, right? Anyway, so let's continue the Stackelberg model. Okay. After that, we are done with the main thing we'll talk about with the game. Okay. So we conclude this dynamic game of complete information with the last example we call Stackelberg combination, which is you learn it from the intermediate micro if you learn it, but we now do it in a proper way, okay, more formal way. So this is just a column model, right? And inverse demand, cost is constant over constant marginal cost, profit is standard, okay? Now the only difference is player one move first, player two move second, okay? How to solve this game? It's very simple. We just solve it by backward induction, okay? And you will ask, player one can choose from 0 to infinity, right? Or 0 to positive number, whatever, right? Then the infinite many sub-game, how can I solve? Right? Because when player one choose one sub-game. Player two choose 2, another sub-game. Player 2 choose 3, another sub-game. How can I solve for each sub-game? Luckily, we can solve the sub-game generically. Okay? We will solve it, say, given player 1 choose this, what player 2 will choose. Okay? We solve infinite sub-game at the same time. You will see. Okay? But this is the approach. Okay? We will solve all sub-game simultaneously. Okay? So, look at backward induction. Okay? Player 2 would say, given what player 1 have chosen, he would choose the production. Okay? So the subgame will be player 1 choice has been fixed, what player 2 is doing, right? Player 2 is just optimization problem, right? The subgame is just player 2 produce the quantity based on what is observed in Q1. Okay? So let's see the game. Okay, backward induction. So it's just saying that, okay, Q1 is fixed number, whatever number, I don't know, but we solve it all the subgame at the same time, so we just generate Q1. Okay, this is what Q2 choosing, right? It's very simple. You just construct the equation. You know the max is in the middle, right? Right. Of course, you can take a derivative, right? You can solve it, right? Since all of you have better math than I do, so you should easily see that. If you want, you can just solve the FOC, right? FOC will be just A minus Q1 minus 2Q2 minus C equal to 0, right? Is that clear? That's how the FOC, right? You take partial derivative with respect to Q2, right? You solve for Q2, is the answer, okay? Now, what does that mean here? This means that this is a strategy for player 2. Why? Because you tell player 2, the firm 2, whatever Q1 was a Q2. Okay? So this is a function, right? Remember, this is very complicated. It's a strategy, not an action. Okay? Given Q1, this is action, right? But I don't specify. It means for every possible Q1, I map it. It's a function. So it's not a simple, it's not action. This is a strategy. If I give you what Q1 is, it becomes an action. Okay? This is strategy. So it's be very, very careful. Okay? Although you don't have to write that down, but you have to be careful distinction in your heart. Okay? There's a function there. Okay? And backward induction imply you put that back to player 1. Okay? We solve backward induction, right? We solve this subgame. Now we go to solve backwardly. Okay? So what we do is player 1 what to do. Okay? Player 1 is actually knowing what player 2 will be best doing, right? He's basically considering Q2 is what he's best doing. Okay? So replace Q2, this backward induction, right? His payoff, replace it by what Q2 best choice, right? Because you know, player 1 would know, I choose this, he will choose that, right? So basically it's 1-to-1, right? So that is choice, right? So that's why he's choosing the best thing, right? Basically it's just like firm 1 is looking at Q2. I know you would do this if I do that, okay? So that means that I would do accordingly, optimize, okay? So you can solve this as the outcome, okay? Now you know player 1 best choice, okay? Best strategy. You have to plug that into player 2 to find out the equilibrium outcome, okay? This is not equilibrium strategy, equilibrium outcome, okay? Equilibrium strategy is still this one, so don't make mistake. Equilibrium strategy is firm 1 choose this one, firm 2 choose this one. This is the equilibrium strategy, okay? But the equilibrium, that's what the subgame of equilibrium, but the equilibrium outcome would be this guy and this guy, right? Firm 1 will choose this, firm 2 choose that. Oh, I don't have graph here. Okay? I suppose a graph, but I don't know why I removed that. But basically is firm 2 is, firm 1 is choosing the best response from the firm 2. Why I don't have the graph here? Maybe I just take it out. But anyway, let's have a short summary, and we'll talk about repeated game after the break. Okay. The short summary today we learn is we know how to solve this game. Okay. I will tell you that throughout my 11 or 12 years of research, basically this is the thing I do. Okay. I basically do this for a living. So hopefully you can also learn that to make a living. So what I do is I look at, of course, more complicated dynamic game. People take turn to make decision, right? And you just do backward induction. Okay. Of course, the art is to set the game nicely. Okay. Who move first, who move second, and that have to be very carefully justified. Of course, if someone have built a model, you maybe just follow it, will be fine, right? And you will see that how you set the timing can be make it very complicated. Even you see this problem, right? Just one person and the other one move can be very complicated. And the solve is very simple, right? Just game backward induction. But as you can see, when you build more and more time, then the model become very tricky. Okay, because when you build more timing and you require backward induction, and that a lot of things can be not very tractable. Okay, and the problem is when you have many time, which equilibrium to pick. Okay, right? As you would see, remember the example we have here, right? And as business PhD student, right? You would think this is more likely, okay, than this one, right? That's what we agree, right? So that means that if you say so, that means that this model is not actually capturing everything there. Okay? You would think there may be something before the entry and enter. the incumbent can do something, right? If we model that, put in the model, then you have a new paper. And that happened actually, a lot of new paper comes out. You see existing model, you look at, they have many equilibrium, and they may focus on one thing and say something here and there. And you think, oh, no, wait, this doesn't, there's some missing there, right? You should add to this model one time before or one time after, add more agent, so on and so forth, and you should give more accurate prediction, right? That's how you build a model. Okay, that's usually how you see how model progress. The early model is very simple, and a lot of paper add this or add that, add one more agent, add the government, add the regulator, so on and so forth, to enrich the model and see which prediction still holds, which is not, right? So that is how you build a model. Okay? That's how I also build a model when I write papers. Of course, that would be what I'm going to say, okay, for this one. As I said, I make living by solving this type of models. So I think it's very, very useful, okay? But of course, I again have to be emphasized very carefully, okay? Because usually you don't write the formal model out, right? The formal model out is usually you don't really write this thing. So you have to be very careful, as I said, is you have to define carefully if this happened, you still have to write down the strategy and the payoff, right? Because sometimes you say, okay, when firm one exit, you don't specify the payoff of payer one, then your model is incomplete and people can pick you up stuff. Okay, and I hope I don't lose you. So after the break, although there's many slides, but don't worry, the remaining slides are very technical. So I'm not intend to cover everything there, but I'll give you the full most of the idea there. There's a lot of calculation about repeated gain, but if you study in econ department, you will spend whole semester for repeated gain, right? Apparently, we're not going to do that, right? We'll give you the main idea, then that should be sufficient for your purpose, because I didn't use it, so I don't think it's very useful. I mean, it's useful in some sense, but there's a lot of technicality there, which I think in business application usually don't need those. We'll give you the main idea there. Okay, so let's a break of 15 minutes and we come back to finish the game. More snacks if you want to.
摸到了你的头发，果然是死掉了。我觉得我的头发还蛮有活力的，你摸一下，让我摸摸。但我因为是漂了2次，我都看漂了，我也是漂了2次。就是有一点，有点这个品牌。就是健康的头发，活着的头发，健康的头发。然后就是马尔代夫，然后我要去哪玩？我主要去马尔代夫，然后那你的这头发完蛋了，因为不能碰开水，然后我已经很尽力把会他们每个下水之前都把头发没办法，因为你要拍照。而且我感觉就是蒸汽里面还有开水，对，洗澡水都是洗的，对。不是，我这是不要开始比较了。都是那种就是一整条的那种。你这个是正统的，他们那些都是外地的。我笑死了。那不行，我不是人什么，我满足了。性爱性可以。没有，我笑死，好恐怖啊！这个，跟我的英文名结合了一下。 哭，对，我没有看这画儿，好像哭，我现在然后你配饰就是为了让他看到背后的，其实你心里都是那个，为什么死自己？是。大家可能不认识我，但你们认识我，都有这个一个圈粉。我们这种同学有做的话，你不懂，然后就叫我人生。每天早上8点起来上班，我每天觉得你发现你为什么得这样？我这样的人上人，可能上人起床了，我都在焦虑，不是梦。应该感觉这个这个是到夜晚，到夜晚我们因为有点忙，不是下午就开始。
谢谢大家，欢迎大家补课的时间。
这个你都看得好准，这个。咱俩帮着买好久。
So quickly, because some of you, I want to ask if you can fill in the most preferred day, because we have December 4th in the morning, and someone told me December 4th afternoon will be easy. But I'll try to see December 4th afternoon, December 5th morning or afternoon, we take the one that ends with 5. Hopefully. No question. Oh, question 1 actually say December 4th afternoon. In the morning we have the makeup already, so December afternoon. Question 2 is December 5th morning, and question 3 is December 5th afternoon. Let me write that down. So Q1 is December 4th morning. Q2 is December 4th afternoon, December 5th afternoon, December 5th morning, and Q3 is December 5th afternoon. So morning, afternoon, morning, afternoon, right? Afternoon, morning, afternoon. So to me, there's no difference because 2 days is a makeup day anyway. So it shouldn't affect anything else, but don't worry, the class will record, and that will be extensive material anyway. So it's not, if you come, then it's okay. If you don't come already, you come everything. So there's no loss of, if you don't have to come. Question 1 is the December 4th afternoon, but December 5th morning, and 3 is December afternoon. So choose the one that try to fit most of you. Is that okay? So I hope you know the question, then maybe so look at the answer. So we have 13 and 4 for the first one. The second one would be like 12 and 5. I just pick the one that fit most of you. 14 and 3. Okay, so you want me to put December 5th afternoon? That's fine, if that is what you want. Is it? December 5th afternoon? But the class will record anyway. So if you want to come, you come. If you don't want to come, there's no loss anyway. Additional material is not included in the exam or whatever. Probably, as I said, just cover something more advanced material that is, I think it's interesting for you to know. But don't feel pressure to come. Okay? You come. You don't come, then I go home. So anyway, so let me book the time. It will be the other one will be December 5th. I try to do it like 2:30 to 2:50 to 5:30, something like that, after the lunch time. Okay. Okay. So try to best fit all of you. I think that. Yeah. Okay. Is that okay? I hope to try to maximize the thing, but it's record anyway, so I don't think too much problem. So now let's continue our journey in the in our game. So with sequential form and simultaneous move. Okay. Now we focus on a very particular game we call with the game. Okay. With the game means we repeat the simultaneous move game many times. Okay. And what we're doing here? Okay? And the idea is actually come from personal dynamic, right? We know the main thing is like, okay, we have defect all the time. Okay? If you play just once. And later we'll try to see, even you repeat twice, third time, fourth time, fifth time, no matter how many times you repeat, it is still defect. There's no way to collaborate. And person dynamic is so common. Right? And that is why we call it evolution, right? Everyone dream, and we cannot escape from that, right? Not until very recently, people start to compete, right? And we coordinate to compete, right? So compete is not a dominant, it's not a masculine, right? We coordinate somehow, everyone compete. If everyone joins, we don't join, right? So how does it happen? Okay. How can you sustain that? Okay. Now the question is below. Okay. So I don't know the Zoom people can listen. So the makeup class will be the December 5th afternoon. So I make it like 2:50 to 5:30, 5:50, 2:30 to 5:50. Okay. So standard afternoon. But anyways, on the Zoom or record as well, so you don't have to feel pressure to come if you're busy. Okay? And it's not including exam or whatever, so don't worry about that. So look at this example again, person dynamic, right? It's familiar thing. If you repeat twice, okay, even though the discovered vector is 1, you will always end up DD. Okay? A very discouraging, right? And that's why we always join, right? Because no way to escape, right? We join from kindergarten, we join from primary school, secondary school, right? Join from Gaokao, and now join from Ph.D. And after you graduate, you all continue to join until you get tenure, and get tenure, you also still join, right? It never ends, right? Until from your, remember, you already joined before you're born. Everyone know biology, right? Right? Even before we're born, you join already, right? You already a winner, one of billions of them, right? Right? Already you're the winner already before you're born. And once you're born, you still join. So why? Like this, right? You keep going. So, and parallel induction imply no collaboration, right? So the problem probably is either parallel induction is wrong, which is hard to accept, or actually we are not thinking about finite period. Okay? There are two ways to think about this. Either we drop parallel induction, okay, but drop parallel induction still don't solve the problem. Why? Because it's dominant solvable, right? So one way economic game theorist thing is actually there's no end game. Okay? Actually later you see we'll call infinitely repeated game. That's a way to model this more appropriately. Okay? Why? Because you can imagine this is a price war, right? Bertrand competition, right? If you expect this represent the price gain, then we should expect every price go to marginal cost, right? There will be nothing more than no firm can make profit, right? Firm will fight every time, but we don't, right? Price war is just occasionally happen, or sometimes even don't happen at all, right? That means that the firm must be collaborating somehow, right? We see OPEC, right? The cartel is very successful, right? So how they can sustain that? So we will talk about that. So how to sustain? It's what we call, if you imagine this is repeating forever, okay? And probably the first question you ask is, before we even solve the model, is what do you mean by infinite? What do you mean by play this game infinitely? Okay? The question is not that difficult. The interpretation is like, if we have a discount factor,
we discount the future, okay? The discount factor can be interpreted as where the world will end tomorrow, okay? With the probability 1 minus delta, the world ends, okay? And that means that when we talk about infinite game, actually it's not saying that we live infinitely. Philosophically means that we actually don't know when the game would end. Then we can sustain collaboration. So the repeat is, what we're thinking is not about we live infinitely, okay? It's saying that we don't know whether tomorrow it ends. And with that, we can see we can sustain collaboration, okay? If we know the end game, when it ends, then we become very naughty, right? But we don't know when it ends, then actually it can help us a lot. Okay, let's see the example here. How can we sustain C and C? Okay, so how can we sustain C and C as a Nash equilibrium, some proper Nash equilibrium? So the easiest way is called trigger strategy. Okay, trigger means a button you press. Okay, trigger, right? What's triggering is if we have been doing well, we continue to collaborate. Okay? And once, if anyone have deviate, then we deviate. Right? That's what happened when the advice for marriage. Right? When the others have no affairs, that will be fine. When found out that the other side have anything disloyal, we divorce. Right? Never recycle. No, 不回收, right? Never forget. Never forgive. Right? Anything wrong, then divorce. Okay? Okay? That is what trigger strategy, right? So this we will show can sustain cooperation, okay? Unless you are very short-sighted. Okay? So let's see. So how can we check this is the case? Okay? Very simple. Okay? We'll check two things. We check Nash equilibrium and check subgame perfect. How to check Nash equilibrium? Okay? Checking Nash equilibrium simply require you to check this one. Okay? You only need to check if you want to deviate from this one. Okay? Suppose the other guy is doing C. Okay? Collaborating. You keep collaborating, you get 4 forever. Right? So which represent by the left-hand side. This 5 should be on the other side, sorry. Typo, obviously typo, right? So you get 4 forever. Sorry, the typo. Okay? And if you get DVA, okay, then you get 5, right, in the one period, and you get 1 forever, right, because you are single, right? You may get gain of have affair, 5, right? You did divorce, single forever, right? 1. Okay? So you just compare the difference, okay? And this is infinite sum. It's 4 for this and 5 infinite sum, right? Here is so as long as delta more than 1/4, then you will do it. Okay? This checking in the first period, right? Because subgame perfection, you have to check your strategy, right? Your strategy involves choice every period, right? So you have to check the second period, do you want to deviate, right? But remember, every period is the same, right? So no deviation, right? And you only need to check if, right? That's it. You're done, right? Because remember, Nash equilibrium is to check what? Given other choice, whether you deviate, right? Right? So that's your strategy, right? So this is, you only need to check along the equilibrium path. That's Nash equilibrium, right? along, assuming the other side doing this, right? Both sides doing that, according to, as the game progress, according to the equilibrium. Anyone will deviate from that. If no, then you're done, right? This is the starting point. The second and the third and the fourth, this is checking natural equilibrium, right? Along the equilibrium path, right? According to the strategy, this is the pay accordingly, and no one deviate. Yeah, that's it. So as long as delta more than a quarter, okay, you think the world is likely to continue more than 25%, right? Then you would be thinking that's fine. Okay? As long as it's not the end of the world, then it's okay, right? Because imagine if delta goes to 0, there's no way you can do it, right? There's no tomorrow. There's no tomorrow. Then you can't really collaborate, right? Because that's what you see, right? In all the movie, that's doomsday movie, right? When the day is going to end like tomorrow, then people got crazy, right? People try to grab whatever, do crazy thing, right? Because they think there's no tomorrow, right? That fit whatever. And, right? And subgame perfect had to be a little bit tricky, okay? Subgame perfect means what? We have to check every possible history, not just along the equilibrium path, okay? You check if someone have deviated, right? The history is like not even that, right? R than CC, right? And do remind yourself that if there's no CC, right? It's not cooperating before, the other guy will choose defect, right? And if the defect, I can't do anything. I would just have to choose defect, right? So that's why this, I check everything, done. So I have to need to be careful. What about the natural equilibrium and subgame perfect natural equilibrium? But anyway, you always screw subgame perfect. So that's why you don't have to worry too much, but I want you to know the difference, right? Because you always look at subgame perfect in this context. So basically, what you do is to track every single possible history, right? If it have been collaborate, then no one wants to deviate. If not collaborating, no one to deviate as well, according to the trigger strategy. So that's done. Okay? Is that clear? So what is this here? Okay? Is even look at in the case where collaboration is not possible. As long as you think there's a future, there's a way to go. Right? And that is what sometimes what we call religion actually help, right? Because you think our life are finite, but if you have next life, right? Or you have heaven, or you have hell, right? Then you will behave well, right? That's not, I make up, this is called the, what we call the Pascal wager, right? Whether you believe God, right? If the small probability God exists, then you want to do well, right? And same idea here, right? Because you believe that there's an infinite life in the future, so you would be doing well. All right? Let's continue, okay? And later we will show you there's a generic proof for this, not only true for this in general, whatever game. The idea is as long as people are patient, then you can support any possible outcome. Okay? Even you can support this good outcome, it means that almost every outcome you can support. So that's a drawback of game theory. We play a game because it doesn't say anything, right? Because you say, if you repeat interact a long time, anything can go, what is called the fog theorem, then there's no prediction, right? Basically, you say everything is possible, right? But anyway, before we do that, we talk about another game, which is also very interesting by itself. It's a personal dynamic game. If you look at this is what we have so far, right? The personal dynamic 445005111 is what we have so far. Now we have another called B. I don't know what it is, but B maybe they go to beach. Okay, don't rob the band. Okay, Forget about it, go to the beach and enjoy free feet, sunshine, wherever, drinking martini, any of that, but anyway, free, right? And by doing this, okay, look at this game, okay? This is a Nash equilibrium, right? We know it already. And you can easily check, this is also Nash equilibrium as well. Okay? The two Nash equilibrium, okay? And so the question would be, okay, if you do barrel induction, the last period must be BB or DD, right? If you just do 2 period, right? Finite period. BB and DD is the only protection you have, right? There's nothing to do, barrel induction. So now the question is, in the first period, what can you do? Okay, of course, you can imagine BB again, that's possible, right? BB and BB at the same time, or DD, DD again, fine, or BB, DD, or DD, BB, okay? 4 combination, right? BB and BB, BB, BB and DD, DD and DD, and DD and BB, right? 2 by 2, right? There's 4 possible choice of subimperfect. Can we do more, right? Instead of repeating Nash equilibrium in 2 times. Can we support the crazy thing here, CC? Right? Can we support that? Okay? The answer is yes. How can we do that? We will say, if you do CC, we will do BB. If not, we do DD. Okay? So it's like, how can we support non-equilibrium outcome in the first round or predictive outcome, which is non-equilibrium, is by saying that if we do the right thing, we go to the beach. If not, we go to the hell. Okay? It's carrot and stick, right? So that's why we discipline ourselves. Right. Do I prove it? Yeah, I didn't do it, but you can check. The strategy is, first round we do C and C. If we deviate, not C and C, in the second round we will do DD, otherwise BB. Okay? Barrel induction tells us this is the second stage we need to check, right? Just to check the first stage, right? The first stage is, if I follow the equilibrium, I will got 3 and 4, which is 7. If I deviate, I become a naughty guy, I get 5, I'll get 1, 6. Right? So 7 better than 6, I will better follow that. So that means that this is what happened when you look at Hong Kong movie in the old days, right? The 2 guys got caught by police, right? And police said, okay, try to confess, right? But you know that, okay, if you confess, right, they may kill your family, right? Or beat up dead, whatever, right? But if you don't, then you get reward, right? Being a good guy, right? So by creating something new there, even though it's not as good as 5, right? As long as better than this one, then you can survive, right? That's how the social norm actually is doing it, right? Where the triad group, right? The bad society or crime organization or whatever is trying to do this, right? Right? If you do good, you become 三好学生, right? You get a good thing, right? And if you're not, then you 变成黑五类, right? Then you get bad, right? So that's how you sustain, right? Is how what they call organization try to sustain itself is trying to create certain kind of reward and punishment, right? So that you can sustain collaboration. Right? So now let me formally introduce the game, okay? And it's very simple, right? It's just a normal form game, right? N, A, and U the same thing, right? The only thing is just a T. T is a number there. The only thing is this guy, right? The only thing is this T, right? T tells us how many times we repeat. That's it, right? Either T is infinite or finite. Of course, we focus on infinite in our model most of the time. Okay. Now the question would be, hey, How do you write this kind of stuff? It's very complicated, right? But the idea is same as before. There's nothing new there, right? It's just like history just depend on what has been done, right? Your strategy depends on history. Second line, right? History, right? History come from what has been done in the past. Everyone's choice. Strategy is depend on what has been chosen for everyone. What are you doing, right? And strategy pro player is just depend on what has been done for everyone. What are you doing, right? And strategy profile is everyone's choice. I mean, I don't think you would actually write this thing out, but that is just formality. And some ideas called the path. Path is the based on the action, what kind of the thing you generate, okay? And the payoff, of course, depends on the path, okay? And you discount it, okay? So I guess we go to the definition, okay? Nash equilibrium the same, right? If you deviate, you have to check it, right? And I just check deviation from the strategy. And that means that you only need to check along the equilibrium path, right? Because you just change yourself, right? The other thing don't change, you just change. If you change one period, what you gain from that. So that is why we call the one-step deviation. It's the way to check with the game. Just check every period of time, do you want to deviate? Okay. And sub-game perfect is a little bit more complicated. You have to check all possible history, even though the history is not along the equilibrium path. So I would take the example for that. So one important result is under some regulatory condition, which you always satisfy in your application, is you only need to check only one period deviation. Okay, you don't need to check very complicated deviation mechanism. And the first result actually we expect is if every stage game have only one equilibrium, even you repeat finite number of time, you can't get something out. Like present dilemma, if you just repeat no matter how many finite time, only defect, nothing can be done. Okay, finite is very different. Okay, but we see the example when we expand the game, we have carrot and stick, then even finite we can support. Okay, so that is important because that is how organizational thing or the policy thing changes, right? And that is actually how Chinese government do, or Singapore government actually do, right? Now we talk about everyone's region, evolution in the primary school, right? And also in the university, right? Now what they do is, in the first few years, right? Actually, you don't know your ranking, right? I mean, in China, right? In the primary school, you don't know what is your ranking. You just know whether you are belong to top tier, middle tier, or bottom tier, right? In CHK, now they don't even the first year. I don't think you can choose not to have grade, pass or fail, for the first year classes. Okay, so in order to avoid Juan, right? Providing this. Okay, so government or regulator can change this game from Juan to no Juan, right? I'm offering something a little bit different. Okay. So this is the main result that actually I think is the most useful thing in here is often said is if you a basic Fock theorem means if you repeat many times, okay, if I have A star, which is the outcome of the Nash equilibrium, okay, you look at the stage game, you find the Nash equilibrium, okay, and the Fock theorem said whatever outcome that is Pareto dominate, this one, Pareto dominate means everyone pay off higher than the benchmark, can be an outcome of sub-game perfect Nash equilibrium. Okay, what does that mean? It means the following. Suppose I have a game, in general, whatever game is, can be more complicated than this one, but anyway, I identify the Nash equilibrium. Okay, and any outcome like this or anything else, as long as each one get more than 1, okay, I can support it as a subcamperfect Nash equilibrium. So that means what? Basically, anything will happen. Okay, this why usually for game theories it consider a negative result, right? Because your model becomes useless, right? Because it's like, okay, everything happen. So what are you saying? Right? It's hard to tell, right? But anyway, that means that if you want to go further with the game, you should add more context to this. Okay, I'll briefly go over the context, but that is the main result. It's saying that anything better than Nash equilibrium can be supported. Why? The idea is very simple. Just like present dynamic, the proof is very simple. Whenever we will do the thing that is not Nash equilibrium, doesn't matter, right? Whenever anyone deviate, we go to the Nash. As long as you care the future, you keep what you're doing, right? Because whenever is the bad thing, you go to the Nash, and Nash is self-sustainable, right? We go to the bad outcome. That is a punishment, right? No matter how tempting the reward is, as long as you care the future, I tell you that if you deviate, we go to hell forever, right? You jump, I jump, right? So you don't jump, right? That's basically what Titanic said, right? Jumping to the sea is a very bad outcome, right? And now let's apply this to the practice, okay? And you will see, although the Fock theorem is very simple, but if you consider a case where the people are not so patient, you will see something interesting. So let's see this example, then this will end our class, I guess. So we have only two firm, okay? Cannot, right? Add up together, market price. To make it simple, no fixed cost. There's constant marginal cost. That's the same we have. Okay? And in the Carnot model, this is what we have, right? It'll be 1/3 for each one. Okay? If your monopoly will be 1/2. Okay? Actually, you should prove it. It should not be difficult to prove that. That part is very simple. Okay? So if you have a problem, let me know. I can show you the proof. No, not difficult to show. Right? Cannot actually reply is both firm choose Q. Right? Now, the question would be, can they get this? Right? Because for two firm, the best case is monopoly. Right? Because one firm, the best is monopoly. Right? Two firm will be, they jointly share the monopoly profit. Right? That's what the cartel, right? It's like a cartel, collusion or cartel, right? Is there any way to do it, right? And the distinction between cartel and collusion. Cartel means they come together, they set the price together, right? But this collusion is implicit, okay? You and I don't reduce the price, okay? There's no formal agreement. But implicitly, you know, I'm not going to lower the price. I know because I lower the price, we lower the price. So we are not going to reduce, right? So that's the idea. Okay. So what is the trigger strategy? Okay, we use the simple one is the Nash reversion. What we call is we support the monopoly outcome. Okay, of course this is not Nash, this is not equilibrium in stage game. But we say that okay, if we have been doing half of the monopoly profit, okay, producing half of monopoly quantity, okay, if have been done in previous round, we continue to do that. Otherwise, go back to the Nash. Okay, so we will produce a quarter, right, for each one. If you are naughty, right, then we produce 1/3. Okay, the monopoly is 1/2, right? Half of A minus C is monopoly. Okay, if you split, actually everyone produce a quarter of A minus C, right? And the Carnot case is 1/3 for each one, right? So you just reduce production. Okay. So how do you solve this model? Okay. I think this is a good illustration. Okay. First is look at if everyone produce half a monopoly, right? Is to produce at this is what's the payoff. Okay. Some calculation I'm not going to do line by line, but just give the idea, right? So this is the profit when you collaborate, right? Half of the monopoly profit. Now the next would be what happened under Carnot, right? This is the Carnot, means under punishment, right? Under Carnot model, right? Everyone produce one third, so the profit is 1/9. Is that okay? And now the first question is, okay, what happened if you deviate in this period? Okay, if the other guy is doing 1/4, which is the monopoly, sharing the monopoly profit, right? What you are going to do? Okay, what's the best thing you do, right? He's doing half monopoly. What's the best thing you do? You calculate what is the gain from deviation, right? So you can calculate this. You get 3/9/68, okay, as a profit. Okay. So this is the game, right? That's what you think. If you collaborate, right, everyone will share monopoly profit, right? So it's this one. Okay. And if the other guy is still doing monopoly, you deviate, this is your profit. This is a gain, right? And this is a punishment, right? This corner outcome is here. Okay. You only need this calculation to calculate, right? Because what you do is in the normal time you're doing here, right? If you deviate, you get punished. We are all here, okay? And this is a gain of deviating in this period, right? So we just need to check this forever is better than you have one period this and forever that, right? So that is the only thing. The difficult part is to figure out this one, right? This is easy, right? Share monopoly. This is easy. Corner forever, right? The only thing is if other guy is honoring the deal, you are not, right? Okay. So you can check that payoff, right? And just as I said, right? Forever good, you deviate, and one period ever, you will get this one. Okay? So let me repeat. This is monopoly, sharing, right? And this is you being a bad guy, and this is punishment, right? You get Nash, okay? You can solve it out as long as delta is high enough, then you're done, okay? And as we said, this is nothing new, right? Because the fourth freedom tells you, as long as you're patient, you can do whatever you like. So this number doesn't mean a lot, okay? The question would be, what happens if your delta is less than this number? That's the key, okay? Because it's easy to see this always hold, right, from the theorem, okay? The main part is look at this one. If less than this, what can you do? Okay? And especially for environmental thing, this is very important, right? Because if people are patient, they will save the earth, for sure. But everyone has finite life, right? The discovery is not as high as we would want to be, okay? What we can sustain. So how do we do this? Is we have to see, okay, monopoly is very tempting, right? You can remember why we cannot sustain this. Is the difference between this is too high, right? So because if you are cheating, if you are a good guy, you keep doing this. If you're cheating, you are going to get this much and this forever, right? For this, you can't change, right? This punishment, you can't change, okay? The only thing is to make this gap smaller, right? So you try to make this a little bit smaller. Okay, that's how we're going to do that. Okay, what we're going to do, because to make this smaller, you make the gain also smaller. Okay, basically you make this gain smaller. So what you're going to do is to try to say, instead of sharing the monopoly profit, actually everyone produce slightly more than 1/4, okay, but not as much as 1/3, right? 1/3 is already the Connaught, right? 1/4 is sharing the monopoly, somewhere in the middle. Okay, so we don't know what's the number, but it called QC there. We figure this out. Okay, and this QC depend on our discount factor delta. Later you will see. Okay, so what I'm saying is, at a good time, we produce certain quantity. Okay, and if we deviate, of course, we will have dividend gain, but we will try to make sure that our collaboration is sustainable given our delta. Okay, let's see. So under punishment, the same. Okay, if we collaborate, this is our production, this is a profit. Okay, and then we have to calculate the deviation gain, the same process. Okay, the same proof. Okay, and just to remind you, what I'm doing here is, this no longer this number. Okay, I'll make sure this number. Okay, this we calculate. Okay, I find the optimal number here. So what I do is the following. Okay, I want to say, okay, if we're doing the good thing, we'll get this forever, right? This forever is like this forever, right? QC forever. If I deviate, of course, depend on QC, this is my deviation, okay? And I will get NAS forever. So I can solve the QC, right, to make it equal, right? I make that continue as same as deviation. Okay, then you can solve it, turn out like this. Okay, that's nothing difficult, but just quadratic formula, right? So it means what? Let's draw the diagram. You will see, very simple. So the simple is like this. If you are very patient, we can sustain monopoly, right? Everyone produce 1/4. If none of us is patient, you go to Connaught, everyone produce 1/3, right? And if you are intermediate patient, you increase. Okay, you're getting more patient, you can sustain a smaller output, right? But you're not that patient, you have to collaborate at a less collusive level. How collusive you can be depends on how patient you are. That's what the graph shows you. Okay, so the formal proof of this, right? Formal proof telling you that the more patient you are, the more collusion you can get. Okay, so probably the question is why I cannot have this efficient outcome, right? Because you're not patient enough. Okay, and that's why a lot of time the society help you to increase patience, right? And you have the retirement fund, pension fund, government give you bonds, so on and so forth, right? To make sure that you don't being opportunistic, right? So that is the idea, right? Just to try to make sure that not so drained, right? To make sure that you got some bonus, make sure that you don't do so bad. Okay, so you can see the graph. It will be, this is the outcome of Connaught, the green one. Okay, last slide. Okay, the blue one is monopoly outcome. Okay, and if you're patient enough, you can be here. But if you're patient enough, then you slightly move to here, right? So that is exactly the diagram you would expect to see, right? If you are good, then you're here. This is the best outcome for them. But if you're not patient, you're slightly moving along the route until you get to the Connaught. Okay, because if you're infinitely impatient, then you get 1/3, right? Is that okay? And I don't want to go to detail, but I just want 2 minutes. Okay, that's okay. 2 minutes. So 2 minutes. Not talk anything about it. This is called the penal code. Just saying that we have a punishment always go to Nash, right? And that is the standard way. But there's a very complicated way to punish you. Okay? And what it's trying to say is, this kind of model is trying to say, if someone deviate, you have a special punishment for each one. Okay? If one deviate, this is the game we play. If two deviate, this is the game we play. But that means, but what they're trying to do is to show you that nothing new. A technical way to say reduce the delta, right? The threshold, because the next reversion require you a much higher delta. If you are able to design punishment for you, punishment for him, punishment for her, then we require less patience in order to support a good punishment. That's what it is. I'm not going into detail, okay? Because this is very technical. I don't think you need it anyway. The other one is called another Fock theorem, even more crazier than you think. But I think this is the last slide, single last slide. I'm not going to talk anything more. So this is a very crazy theorem. Is the Nash reversion, the Fock theorem is that anything better than Nash can be supported, right? And here even more extreme, even better than that. Okay, what we call the resolution payoff, the min-max outcome. Okay, what is min-max? Is other people are the world's against you. Okay, everyone try to do harm to you, try to minimize your payoff. Okay, and I can do whatever, right, to against this. Okay, they minimize me, I maximize it. Okay, that is the payoff is called restoration. Is the worst thing, the minimum I can guarantee, because no matter what you do, okay, I can find the thing that's safety bottleneck. Okay, this is what we call the restoration payoff. Okay, they call the min max, right? The maximum you can do, they try to minimize you. Okay, and you don't worry about this part. But what it said is anything that's strictly better than restoration payoff can be subscale perfect. That means that again, anything can go even further. Okay, so that means that of course you ask what happened in the current game theory is that many things can be done, but it's trying to reduce this set because this set is too large, right? Everything go. So that's why you add more stuff. I'm not going to talk about, but you can check it by yourself. It's many things that here. I'm not going to talk anything, but that's last slide is we'll call monitoring. Okay, I don't have time. What he said is in the game that you can support any outcome is because you can detect the other guy is defect or not. Right? If you can't detect, then it's much more difficult. Right? Suppose you kind of cartel, right? With collusion on a price. If I don't know the other guy actually cut the price, which may be due to economic fluctuation, then it's more difficult to sustain, right? Because to sustain collaboration, you must punish those who are bad guy. But if you cannot pinpoint who is a bad guy, you cannot punish. But if you're not punishing, then people want to deviate, right? It's like you have to know that there's a difficulty there, right? So that's why a lot of studies after this is game theory is focused on there's a monitoring technology is different. You can't tell the others have deviated or not. Then how can you sustain? How do we sustain? Right? There are many things you can do, but it's out of the scope of our class. But what it's doing is try to reduce the set, right? Because of you can't tell the other guy have defect, you have to come up with a sophisticated way to handle it. Okay? And the set is much smaller. And that is what they are doing, right? Because yeah, I'm not going to talk about any more about that. Okay, and I see you next week.